In this session, we will derive the drain current equations of MOSFETs using the Gradual Channel Approximation model. The analysis will start with NMOS transistors, and then we will extend the results to PMOS by considering the necessary sign conventions. We will examine all operating regions, cutoff, linear, and saturation, including the important effect of channel pinch-off in saturation. Consider cross-sectional view of the N-channel MOSFET. The source voltage and bulk voltage are 0V. VGS and VDS are controlling the drain, channel, current ID. VGS is applied greater than VTH so that channel is created. X direction is taken perpendicular to surface, pointing towards the substrate, and the Y direction is taken parallel to the surface. Source side of channel is taken as origin, 0, 0. Electric field along X-axis is X and along EY is EY. The GCA model is based on certain simplifying assumptions. The horizontal electric field along the channel is much smaller than the vertical electric field induced by the gate. So the drain current is following in channel in Y direction only. We use the charge sheet approximation, meaning carriers are confined to a thin inversion layer. The carrier mobility is assumed constant under low field conditions, and the source is taken as the reference terminal. These assumptions simplify the mathematics while keeping the model physically accurate for long-channel MOSFETs. At any point, X in Y-axis, along the channel, the inversion charge density depends on the gate voltage, threshold voltage, and the local potential at that point as depicted in the equation. The effective voltage available to induce charge reduces as we move from the source to the drain, which explains why the channel gradually tapers off as the drain voltage increases. The drain current is calculated by multiplying the inversion charge with carrier velocity. The velocity is proportional to the electric field, which is the derivative of channel potential. Substituting and integrating from source to drain gives us a quadratic relationship for current in terms of drain voltage and gate overdrive. This equation is valid in the linear or triode region. For a fixed VGS, then IDs depends on VDS. VDS-2 has a smaller effect on IDs at low values of VDS since it is not multiplied by very small thing. The VDS-2 term alters the function shape in the linear region. As it becomes large enough to significantly decrease IDs in this function, the transistor enters saturation and this expression is no longer valid. MOSFET I-V characteristics. Linear region. Since we know what the current will not decrease as VDS increases past VDSAT, we can use this expression to define VDSAT. In the saturation region, as VDS reaches VGS-VTH, the channel charge at the drain end vanishes. This condition is called pinch-off. The pinch-off point moves slightly back towards the source as VDS increases further, effectively shortening the channel. While the current ideally saturates, in reality, it increases slightly due to channel length modulation, modeled by the factor 1 plus VDS. This effect is analogous to the early effect in BJTs. The MOSFET has 3 operating regions. In cutoff, no inversion layer exists. In the linear region, current rises quadratically with VDS. In saturation, the current ideally becomes independent of VDS, but in reality, it increases slightly due to channel length modulation after pinch-off. For PMOS transistors, the same derivations apply with sign changes. Gate to source and source to drain voltages are reversed, and the threshold voltage is negative. The resulting current expressions are structurally the same as NMOS but account for these sign conventions. Graphically, the MOSFET I-V characteristics show quadratic rise in the linear region and saturation at high VDS. In practice, the curves in saturation have a slight upward slope due to channel length modulation. This shape is essential for analog applications like current sources and amplifiers. For NMOS, the ID versus VDS is in first quadrant and for PMOS it is in third quadrant. To summarize, the gradual channel approximation provides a framework to derive MOSFET current voltage equations. The 3 regions of operation are well explained by this model, with pinch-off explaining saturation and channel length modulation refining the real behavior. Both NMOS and PMOS devices follow the same equations with appropriate sign changes. In this numerical example 1, We are calculating the drain current of an NMOS transistor using the Gradual Channel Approximation model. The first step is to identify the region of operation. We calculate __, which comes out to 2.2 volts. Since the applied _ of 2.5 volts is greater than this value, the MOSFET is operating in the saturation region. Next, we substitute the given values into the saturation current equation, equals 12 mu ___, caret 2. After calculation, the current is found to be 4.84 milliamperes. This demonstrates how we can apply the derived equations to solve practical MOSFET current problems. In this example 2, we are given 6 measured operating points for a MOS transistor, 3 with source-to-body VSB equals 0V and 3 with VSB equals 3V. Our goal is to identify whether the device is NMOS or PMOS, then extract the process parameter Kn, the zero bias threshold voltage 0 Vanuatu, and the body effect coefficient gamma. We will assume the gradual channel approximation and use the saturation current model ID equals 12 Kn, VGS Vt, caret 2 in the regions where the device is in saturation. The Fermi potential given is F equals 0.3V, F equals 0.3V in the body effect term. From the data, when the gate-to-source voltage increases from 3V to 5V, the drain current also increases significantly. This is a clear indication that the device is NMOS, since in PMOS devices the drain current decreases when VGS increases. We apply the standard quadratic saturation model ID equals 12 Kn, VGS Vt, caret 2, which is valid when the device is in saturation, pinch off. The threshold voltage shifts with source-to-body bias according to the body effect relation. Note that when VSB equals 0, the threshold reduces to the zero bias threshold 0 Vanuatu. We will first use the 3 measurements with VSB equals 0 to extract Kn and 0 Vanuatu, then use the VSB equals 3 data to obtain gamma. Using the 3 measurements with VSB equals 0, we fit the quadratic saturation expression to find the process parameter and zero bias threshold. A least squares fit yields Kn almost equal to 60.0 AV caret 2 and Vt0 almost equal to 1.201 V. Can have a consistency check. Substituting these values for VGS equals 4 reproduces the measured ID, almost equals 235A, confirming the fit. Now we use the 3 measurements taken with VSB equals 3V to compute the effective threshold voltage under body bias. Rearranging the saturation equation gives Vt equals VGS sqrt root 2 ID Kn. Using Kn equals 60 AV caret 2 produces nearly identical effective thresholds for the 3 points, almost equals 1.598 V, demonstrating good internal consistency of the data. To obtain the body effect coefficient, we substitute the extracted thresholds into the body effect formula. With Vt, 3, almost equal to 1.5984 V and Vt0 almost equal to 1.2010 V, and using F equals 0.3 V, the root difference term evaluates to about 1.12277. Solving gives gamma almost equal to 0.354 /F caret -1/2. In summary, treating each measured row as an independent operating point and using the saturation current model, we conclude the device is NMOS. The extracted process transconductance is Kn equals 60 AV caret 2, the zero bias threshold is Vt0 equals 1.201 V, and the body effect coefficient is gamma, almost equals 0.354 V caret 12. The near equal effective thresholds obtained from the VSB equals 3 data confirm the self-consistency of the extraction. For greater accuracy in practice, one would take more measurement points and apply a formal least squares regression.